Welcome to Iron a show about Targetable database, which is not broadcasted on Twitch every Thursday at 5 p.m. UTC, because for the last 3 weeks I'm having super unexplainable problems with Twitch. But we continue to record show still in a highly available manner, and you should be able to catch up, or if you wish to stay sync to the current state, watching the recording on YouTube. Okay, so let's get started, I guess. Yeah, so my plan for today was what I told you last week, that we are going to stop discussing consensus and we are going to start discussing LSM storage. But today, when I was preparing for the recording, I had this unknown consensus bug to fix, and I was like, okay, I just need to quickly fix it in half an hour so that I can then talk to you about LSM. And then it dawned on me that that might actually be not a good idea to just, fix a bug in consensus. It might actually be more interesting to debug this together with you so that I can also explain our magic simulator. And that's what we're going to do today. We're going to try to debug a real bug from the main branch of Targetable. I don't know whether it is an easy bug or a hard bug. Maybe, I've been we'll be recording this for 10 hours straight, or maybe there's going to be winter, summer outside several years, but hopefully we'll crush it in less than an hour. Okay, so let's get started. And before I actually start showing you the simulator's code, let's just look how, that was too fast. Let's look how the bug actually manifests itself. So inside Targetable directory on this commit, I'm going to run this command, zig build simulator run -release -- and the random number generator seed for the simulator. And the trick about the simulator is that it is fully deterministic. So I'm pretty sure that this thing here will finish with the same error that our fuzzy server found. Okay, and while this thing is running, and it will take some time for it to finish, let's increase font size. Font size increase, font size increase, font size increase, font size increase. Okay, that is better. Yeah, while I think on the left is running, let's actually look at the code which is running here. This is simulator.zig, and this is like, standard separate binary, which uses Decoding itself, and more crucially, which uses this cluster thing. Okay, where is the cluster? Okay, yeah. So this cluster is going to actually be like the brains of the simulator. But let's take like a quick high-level look here. So yeah, first of all, the only argument that is passed on the CLI to the simulator is this random seed. If no argument is passed, then we use random seed. Otherwise, we pass a number from the argument. That seed is then fed into pseudo random number generator, and that defines the whole simulation. Okay, then in an instance of finally this whole simulation thing finished. So you see that like it said that we have a crash here. And what's interesting here is that, again, this simulator simulates the whole cluster. You see that there are 9 machines here, 4 active replicas and 5 standbys. And we see that the issue, which is reported by the simulator, is that we don't have liveness. That these machines, we weren't able to process. They are like basically live locked. They are unable to process transactions. So as you see, it took us a long time to like actually go and run this thing. This is because, yeah, kind of like liveness bugs are not easy to detect in this simulation mode because, well, maybe we just need more time. So the way we detect liveness bugs is that we basically like run for a lot of time, and in the end we give up. If we want to debug this, we would actually like to reduce the time we run the thing, because hopefully it will still reproduce the result, but we'll spend significantly less time figuring this out. So this is determined by this tix max requests parameter, and let's make it 40 times smaller, but still check that the thing basically reproduces. Okay, so again, back to the simulator. Using this random number generator, we create all kinds of parameters. So we determine the number of active replicas, the number of standbys, then like various things like how flaky is the network, how faulty is the storage. State machine should be compiled. Okay, yeah. We also have 2 potential state machines, so we could run like the real accounting state machine, or for consensus specifically, we could run a smaller, simpler echo state machine. But this one I think is using the real one. Okay, then we ask to generate workload. So basically the sequence of transactions, the sequence of accounts and transfers we are going to shovel through our system. And then we actually, okay, let's take simulator options, a lot of simulator options, and we actually need the simulator. So the core of the simulator is defined in this same file, is actually this cluster thing. So this cluster is what allows you to, okay, so it compiles, it takes unreasonable amount of time to compile. Hopefully one day Zig implements a backend which is faster than LLVM and compiles a code which performs almost as fast. But well, for now we're just going to wait. Okay, so this is the cluster. And because it is a cluster, it actually manages a whole array of replicas and a whole array of the clients. And the way this whole thing is driven is through this take function in the simulator. So let's go back to our main loop. Like this is the how it occurs. So we try, like we want to process all the requests, and we go and we tick the simulator, and this tick is what. Okay, where are we? Okay, we finished. Okay, perfect. So this now should be significantly faster. If we subtract completion time, we should be finished pretty soon. What's on status? Okay. So yeah. And after we tick, we basically checked whether we are done, whether we replied to all requests, and if we also do an upgrade, something which was implemented last week and which I'm not going to talk about today. We also want to check that all upgrades are done. Okie dokie. So, what's simulator tick? Well, it's basically cluster tick. And the cluster tick is essentially network tick and then storage tick. And the storage tick is that thing that's going to drive each and every replica, because we have a storage for replicas, so a separate event loop per replica. And the network is the thing which is responsible for delivering messages between all the replicas. Okay, so probably if this were really a video about explaining how simulator works, I would actually go to explain network and be kind of a hood and look at resistant storage and whatnot. But I'm actually more interested in trying to debug this failure we have on our hands. So let's leave it at that. Let's kind of like treat simulators like abstract thing that can run the whole cluster. So how we further debug this? Well, we need to understand what the hell is this output. It is actually documented. There is like testing.md file, and it contains this nice infographic, which actually I didn't know existed. And basically I only learned about this when I was like changing this output format, and DJ told me, hey, Alexei, could you update the docs? And I was like, oh my God, we actually have docs here. Was too little too late for me. But well, now that you're watching this video, you can actually avoid reverse engineering this format and just look at the docs. So, first thing first, each line corresponds to a single replica. And this leftmost column is the ID of the replica. So you see there are like 9 things here. The next column is the role of the replica. So this is a backup, like kind of like the backwards slash looks like a replica is leaning onto a wall. So it is a backup. And the forward leaning slash is the primary, because, well, it goes forward and it leads everyone else. And then this hash sign is the crushed replica. Then we have status. That status from consensus protocol, which is like either normal or a view change or recovered head. So H is recovered head, V is view change, and hash is crushed. Then we have the view number. Then we have checkpoint number, commit min, commit max. Then we have state of the journal, how many faults are there in the journal. Then this is well prepared. I always like confuse while and journal. Like I still don't understand like which is which and why they're in it. And then we have like some extra columns which hopefully won't be necessary for us today. Okay, so one thing I wanted to do here is that, you know, like kind of like we crashed in the middle. We crashed when one replica was crashed, other replica was in recovery at head state, they all were rechanging. So this is kind of like what you get when you stop simulator in the middle. I would like to at least get in a situation where all the replicas are online. So to start debugging this, let's go to this ticket code and say that if our tick is less than, say, well, 500,000 sounds good to me. We are just going to say that the replicas are not going to crash anymore, and replicas are going to restart pretty quickly. So hopefully, this will get us much easier state to debug. And while we are at it, let's actually try to get the full log here. So you see that the printout here is like pretty Spartan. We only print things or like major state transitions, like for example when a replica commits something. There is a build time option, simulator log equals full, which allows producing, well, full output log, but it is going to be extremely verbose. That's why I'm just going to redirect to a file, and then we're going to try to parse that file. Okay, I really wish LLVM in release safe were much faster, but well, you gotta work with what you have. Okay, so basically the next plan is, well, first of all, I verify that my hack to get into state where all replicas are up works, and then we are going to grab the log. Okay, yeah, okay, we've even managed to crash on the view number 700. Which is pretty neat, nice number. Okay, so while we are outputting the log, let's take a look at this situation. So, well, one replica is recovering head. To get out of recovering head, you need a primary. So this is understandable, and like the rest of the cluster cannot get into the primary. So let's just like forget about replica 0, because it isn't really relevant here, because here we have like 3 replicas, and 3 out of 4 replicas should be enough to do more or less anything in the cluster. Okay, all of these replicas actually seem pretty fine. They all have checkpoint 95, and they all have committed ops up to 106. But they also have this curious op 107, and apparently they are unable to commit to separation. And oh my god, is this? Oh, interesting. So this actually might be related to the upgrades feature, which we have recently implemented. Or hopefully I will not have to debug upgrades here, because that's going far beyond what we've covered. But well, we'll see. Okay, so yeah, but like you see, like they committed up to 106. But they have 107 in their log. So apparently something's up with this 107. So they cannot commit 107, and additionally, it looks like 107 for some reason prevents replicas from doing a view change. In the meantime, we've computed our log file. And as you see, like the log file is like 4 gigabytes. So it ends with the same thing as this thing here, and this is like the magic of determinism. You see, the result is exactly the same on the left and on the right, but I run this with different log levels, and I wouldn't be able to do this if my code wasn't like 100% deterministic. Okay, perfect. So, but you see here, like besides like the standard output, there's like a lot of like printouts for like sending messages, delivering packets, and whatnot. So we're going to find the answer to our question in this log. And well, if I were a true Unix graybeard, I would do this with like vi, grep, set, and whatever, but I'm not. I'm going to use this little tool I wrote, window, which allows me to look at these logs. Okay, so how this tool works? Well, it kind of like it is a bounded grep. So you see we have log whopper, which is the input file to this tool, and we have a log whopper.window, which is the result. And the constraint of this tool is that the result is always going to be bounded. So if I ask to look like anything concerning replica 2, it will like run the equivalent of grep, but it actually won't find everything. It will find only like 4 kilobytes of data. And I can make it faster, larger. I can say, okay, I want like up to 500 lines of output, which will give me 100 kilobytes of output. So you see, this is with default settings, and this is when I bumped a number of lines in the output 10 times. But kind of like the thing here, like the core idea is that as a human, I cannot read more than a single screen of data. So I just ask my tool to not produce more than a screen full of data, and that allows the tool to be pretty fast. Okay, so let's start with going to the very end. So we switch position to 100%. Yeah, that is the thing here. Okay, so op 107 is suspicious. So let's look what happens with that op. Okay. So let's also, okay, apparently replicas try to repair op 107, and it is missing on, okay, let's actually, we know that from here, we know that like replica 0 is recurrent head, so we can just like completely filter it out. So this, well, by the way, in the logs, this is the number of replica. So we could say that we don't want to hear anything from replica 0. Okay, that leaves us 1, 2, and 3. And okay, 2 says that this is missing, and 3 says that this is missing, and 1 says it is written. Okay, let's also scope these to replica 1. Written, grabbed header after read. Okay, that's interesting. So what we see so far is that we have this operation 107. It is present only on replica 1, and it is corrupted there. And replicas 2 and 3 seems like they don't have this prepare. Okay, I think okay. Okay, that's nasty. I think I might have debugged this. Yeah. Okay. Okay, so sorry, I'm thinking much faster when I'm speaking. Okay, so let's see. Okay, so this is exactly what I was talking to you about when we discussed this view change protocol in the face of disk failures. So if the disk fails, like if there is a probability that you write something to disk and then you cannot read it, then during consensus, it is important that you do not just blindly take the latest data you have. Because if the latest data, like the latest prepare, like OP 107, were present only on a single replica, and that replica's disk got corrupted, then if you try to add that OP to your consensus, your consensus is going to be deadlocked because, well, the OP was replicated only to a single machine, and that machine got corrupted, and the OP is no longer present anywhere in the cluster. So what you want is you want to have truncation logic. You want to take the operation if it, if you know that the operation, if you positively know that the operation wasn't replicated to a quorum of replicas, you want to proactively truncate it. And this is kind of like what we want to do here with this operation 107. Because, well, it seems like this operation is only present, only replica number 1 has this operation, so it should be safe to truncate. But then we have this replica 0, which is recovering head, so it is like absent from consensus, and it might or might have not prepared operation 107 as well. This looks like a case where the cluster is correctly getting stuck. So let's see if we have any prepare case for operation 107. Prepare, okay, and let's start with position 0. Okay, what do we have here? Why we don't see anyone preparing basically anything? Okay, 10, 80. Okay, let's bump the number of source bytes. Okay, so let's start with this position then. Go up a little bit. Okay. Then presumably we had some kind of a bad crash where a lot of ticks were required to. Okay, yeah, I think that's it. We now positively know that there was only single prepare OK sent in response to operation 107. So we, looking at the whole state of the cluster, we actually know that this operation is safe to truncate. But from the cluster's perspective, because there is this single recovering head replica, it actually isn't safe to truncate it. Okay, so let's start with this position. Okay, I deleted more zeros than I wanted to. So this is 100 max is okay. Okay. So yeah, this is interesting. This is the place where stuff starts going south. And let's look how DVC looks started from this change. So okay, let's start with this thing and look at what is happening here. Okay, so replica 1 receives a DVC. Okay. So replica 1 receives a DVC. It receives DVC messages from itself, from replica 2, and from replica 3. The, DVC of each replica includes two headers, 107 and 106. Replicas 2 and 3 NAC of 107, and replica 1 does not NAC it. Well, because we have seen prepare OK, it is actually correct that it doesn't NAC it because it would be invalid. Basically, kind of like this is what NAC means. NAC means that replica has never sent a prepare OK with this message. Okay. So if we look back at DVC quorum headers function, this is the function, like DVC quorum headers, which gets us of 107 in the CU. Because when computing NACs, based on these three messages, the of 107 will accumulate only 2 NACs. But because we are in a cluster of 4, we need at least 3 NACs to actually be sure that the operation is not committed. But we only have 2 because the third one is from this recovering head replica. So okay, this sounds like a case where a cluster is correctly unavailable because it is genuinely not sure whether op 107 could have been committed or not. The question is, well, why then the simulator fails? The answer is that generally the simulator tries to maintain less than threshold of failures. So with 4 replicas, the replication quorum is 2. So the simulator will take care to not corrupt a single message on 2 replicas simultaneously. Because if you have 2 corruptions, game's over. But this doesn't work for recurring head replicas. So it might be the case that a prepare is corrupted on one replica normally, and a different prepare is corrupted on the different replica, and that replica then goes to recovering head state. Okay, so let's confirm our corruption hypothesis. And let's look at what is actually being corrupted. Okay, so we have, well, this corruption happens before we get the corrupt header. So presumably this is different. So this is prepare all for all 107. It's actually freaking awesome that the input to this window tool is just a text file, because, well, now you have commands, and with commands you like essentially implement it and do without creating a custom CLI interface. Okay. Actually, I don't need anchor here. Okay, and let's start with position 0. Okay, okay, so what I'm trying to do now, our log is a ring buffer. And prepare with op something goes to the slot number something modulo the length of the ring buffer. And I want to figure out what is the slope for op 107 to trace this corruption. So let's quickly look at this. Okay. Actually, okay, you see, I have conveniently saved this position. So we should see here a slot. Slot. Why it is? Why it is so? Okay. Okay. Yeah. This sounds more like it. Well, yeah. It actually makes sense. So that this position is position for when we send prepare OK. But if we're sending prepare OK, we have written data at risk before that. And, well, the slot is printed before that, so that's why documenting here gives us this slot. So slot 11. Okay, then we can get back to. Okay, yeah. See, this is corruption. This is a corruption that the simulator injected, which caused us to miss this header. Okay, great. Now I want to explain why replica 0 is in a recovering head state. Okay, so let's. That probably happened before this. So let's. How is it? Okay. Let's filter in a replica 0 and look at all corruptions. And we'll start from 0. Corrupting sector. That's actually interesting. I don't see any corruption. I don't see any corruption in the write-ahead log, which would cause this replica to go to recovering head. Well, maybe it is recovering head because. I think I get it. Okay. I think so. There are like two cases why we can get in recovering head state, which warrants entire separate episode of Iron Beetle. But well, so one case is that you get a corruption in your write-ahead log, which prevents you from knowing what was the latest operation that you have accepted. Another case is that you have state synced, and after a state sync, your checkpoint is far ahead of your current state, either in terms of view or in terms of operation. So let's see where it goes to recover green head. No, I don't need previous recovering head. Actually, do we actually have logs here? Let's see. Transition to recovering head. So probably it just happened later, maybe significantly later. Oh, no, not 50 bytes, 50%. Okay, yeah, this is something where I want to just, you know, grab it. Okay. Okay, yeah, this is where this happens. Well, this happens only once, so let's just brute force find this position. Okay, let's start here and let's go back to reasonable buffer size so that it doesn't lag. And actually, let's maybe transition a little bit before. Well, okay. So, okay, I'd love to write something like minus like 100 lines here, but that's not supported in window tool yet. Yeah, pull requests are welcome. Okay, so I want to see what is happening before that. Okay, 6. How do I even? Oh, okay, I know the trick. Okay, so this is what happens right after we transition to recovering head. And if I reverse this, I get what happens right before we transition. So if I say something like this, yeah, okay. So before that, it looks like, we do this due to state sync. Okay. And why is there sync dispatch? Okay. So position to recovering head state. Okay, yeah. So that's basically why we are transitioning to recovering head state. Too bad we aren't logging. Hey, too bad we aren't logging why we are doing this. Or maybe we do log this. Okay. Let's take a look again here. So well, yeah, okay. This is a situation. So one missing bit here is that we don't see the head op of the replica, and this is the head op. So the replica state synced. Its head is before the checkpoint, so it goes into recovering head state. It prevents it from participating into view changes, and that kind of like creates this like second fake failure, which prevents a view change from complete. Okay, so in less than 1 hour, I think I actually fully debug this and I fully understand this situation. So let me try to retell the story here. Okay, everything is fine in our cluster, and then replica 0 starts to lag behind. It maybe gets disconnected, maybe it crashes, whatever. The rest of the cluster moves ahead. So when replica 0 gets back online, it goes and state syncs to the current state of the cluster. And because zero's op head is only 42 and the checkpoint is 95, this violates the invariant that, well, checkpoint, that the op head is greater than the checkpoint. So the replica kind of like is a quick hack, which we should fix, goes to a recovering head state, waiting for the start view message to learn about the true head of the view. At the same time, the rest of the cluster, something happens, maybe bad network, maybe someone crashes, goes to a view change. And there is this op number 107, which was accepted only by a single replica, only by replica 1. Only replica 1 sent a prepare key for this operation. But given that replica 0 is in recovering head state, and given that replica 0 doesn't participate in a view change, although it has never accepted the operation, the rest of the cluster actually is unable to use that information. They don't know this. This is the bug in the algorithm. So that means that the rest of the cluster, when faced with a view change, they kind of see, okay, we have 3 over 4 replicas participating in a view change. One replica said that it sent prepare OK for op 107, and that means that we cannot truncate it because the replica which doesn't participate in a view change might have accepted that op 107 as well, and op 107 is potentially committed. So we're going to add this to the canonical sequence for the next view. But surprise, the op 107 is actually corrupted on that single replica which accepted prepare OK for it. That means that okay, lost my train of thought here, sorry. Yeah, basically, that replica could have accepted, the replica 0 could have accepted op 107, so we must add it into view headers for the next view. But then, when we actually try to get the actual prepare for this header, we realize, okay, that the prepare is corrupted. And so we get stuck. And the fix would be in sync superblock update callback here to do something smarter. So kind of right now we transition to a recurring head state, kind of basically as a quick way to get the state sync work. So ideally we should kind of realize that, hey, we have a checkpoint, so let's try to maybe not transition to recover head state and try to recover head state in some, try to recover the head in some other way so that we remain available. And kind of well, it's a quick hack. I think if self status is normal and op is below the checkpoint. And I think this is also kind of like again, writing the correct condition here is going to be hard, but okay, let's leave it at this. So if this is the case, maybe we should try to self op equals self op checkpoint and self replace header self superblock vsr state superblock working vsr state checkpoint header. I think this might get us out of the bank here, provided that we actually recovered into the normal state. I have a pull request in progress with like a proper fix here, but it is not finished yet. But let's see if this quick hack where we just like add this header from a checkpoint works. Okay, it doesn't compile because it wants a pointer and I'm giving it the whole thing. Okay, let's then quickly run cargo check. Well, not cargo check, Zik build check to. Okay, now it compiles, and let's now run the full simulator. And see. Oh yeah. By the way, if you are curious about that window tool, it is right here. So this is kind of, if you have the same problem as me with like multi-gigabyte log files and you cannot grep, then consider giving this thing a try. It's like super rough. I'm not wanted to maintain it or anything, but it definitely helps me solve this particular problem. Okay, yeah, and LLVM is horrendously slow as usual, but we'll see. Well, we've done our job here. We understood what's happening there. Well, I wonder why it is like this slow. Well, actually, yeah, we have like we use Zik 0.11, and that has some pretty nasty accidentally quadratic code when calculating offsets of fields. So hopefully once we update to the next version of Zik, which I really hope Andrew will release sooner rather than later, our compilation should be faster. Okay. Yeah. Sorry. Can we do something useful while LLVM is compiling? I don't know. What have we cluster? Obey on master. Okay. Okay. Finally. Let's hope that. Let's hope that. No. Okay, yeah. Well, my quick fix didn't work, but at least we understood the problem, and hopefully soonish I will be able to land like a proper fix which carefully handles all the cases. Okay, hopefully that was entertaining. At least that was entertaining to me, and this episode shows you how to use deterministic simulation to debug consensus bugs. Probably, yeah, we should at some point do a deeper dive into how this simulator is implemented internally. But let's postpone this, and let's next time, pinky promise. Next time, pinky promise is going to be the end of consensus, and we'll finally go to LSM 3. Thank you for watching this on YouTube, and hopefully we'll get Twitch online back at some point as well.